Alright, in this video we're going to talk about how to solve a simple exponential equation. So what I mean by a simple exponential equation is one that you can write in a certain form. It's when you can get one side of your equation as a base raised to a power, and then the other side of the equation is that same base also raised to a power. The powers don't have to be the same, but the bases have to match. Right, so if you ever have an equation that, or an exponential equation, remember exponential equation means the variable, the x in this case, is in your exponent. Right, so if you have an equation where your variable is in the exponent, if you can get the two sides of the equation to have that same base raised to a power, you can use this method to solve, and we call that a simple exponential equation. If you cannot get the two bases to match on both sides of the equation, then there's a more complicated method for solving that type of exponential equation, which is something that I'll talk about in another video that I'm going to do. All right, so a couple examples here. If I have 5 to the x equals 125, right? When I first look at it, I don't know if it's going to be one of these simple types or whether it's going to be one of the more complicated types. Obviously, this one's going to be the simple type because I just told you that's what we're going to do in this video. But if you're just solving equations for the fun of it, like you don't know when you approach an equation, is it a simple one or is it more complicated? So first thing you should do when you see an exponential equation is think, well, I have a 5 raised to a power over here. Can I change this side of the equation to also be a 5 raised to a power? Well, in this case we can, right? Because 125 is equal to 5 to the third power, right? 5 times 5 is 25. 25 times 5 again gives me 125. So I can rewrite that 125 as a 5 raised to the third power. And now that I have that, both sides of the equation involve a 5 raised to a power, that tells me that it's one of these simpler types of exponential equations. And it's really simple from this point to solve it. Right? The explanation of why we're able to do this is a little bit more complicated, but what we actually do is when the bases match, so just on this side of the equation is just 5 raised to a power, on this side of the equation it's just 5 raised to a power. If the bases are the same, that means the exponents also have to be the same. Right? So it's almost, you can think about it as the bases cancel each other out, or you can think of it as just the exponents have to match, and I get x is equal to 3. And that's it. That's the solution to my equation. Right? If I plug back into the original 5 raised to the third power, that does equal 125. Right? So that's like the easiest type of exponential equation. This is a 5 raised to a power. I can change this to also 5, in this case to the third power. When the bases match, you set the exponents equal to each other. Now, the reason why, if the bases match, the exponents have to be equal to each other is because exponential functions are one-to-one functions. Right? What I mean by that, and I did a video about one-to-one functions a while back, so you might want to check that out if you haven't seen it. But a one-to-one function means it's a function, which means for each x value, you only get a single y value. Right? For each input, you only get one output. But one-to-one means that for each output value, you only get or each output value only comes from one input value. For each y, there's only one x. Right? So one x to one y from one x. That's what we mean by one-to-one. So since this function is one-to-one, if 5 to the x equals 5 to the third power, well, if those outputs are the same, that means the inputs also have to be the same. Right? That means x in this case, that means that this exponent has to equal that other exponent. Right? If it was not a one-to-one function, that would not necessarily be true. Right? I might have a couple different numbers that I could plug in that would give me the same output as the other side of the equation. But since it's a one-to-one function, the outputs of each side of the equation are the same, the inputs also have to match up, which means my exponents have to be equal, and x has to equal 3. All right? So if you didn't quite understand that explanation as far as a one-to-one function, it's not that big of a deal. Maybe to help your understanding, if I draw the graph of 5 to the x power, it's going to look something like that. All right? So if I know that, some x value, if x equals 3, it gives me 125. So here's 125, here's x equals 3. Right? Well, since this graph only passes through 125 one single time, that means that if this x equals, well, if the exponent is 3, I get 125. Since it only passes through 125 once, the only way I get 125 is if that exponent is 3. Therefore, the x here has to be 3. Right? If this graph went back down again, and there was another point where x equals where the output is 125, then I don't know that this exponent has to be 3. It might be the one that's over here instead. Right? But since the graph only passes through that y value once, I know that the inputs have to be the same. Right? Maybe that graph helped a little bit, hopefully, with understanding that. But even if you don't understand what I was just talking about as far as why this works, all you have to do to solve these equations is, if the bases match, set the exponents equal to each other, and then solve if you need to. All right, so the next one down here, example B, we have 5 to the 2x equals 5 to the x plus 1. All right, so one side of the equation is a 5 raised to a power. The other side is the same base, 5, also raised to a power. So the bases don't matter now. The exponents have to match. So 2x has to equal x plus 1. Right? So two sides of the equation, if the bases are the same, I ignore the bases. I set the exponents equal to each other. 2x equals x plus 1. And now I solve this equation for x. So if I subtract x from both sides, right, 2x minus x is going to give me a 1x. So I get x equals 1. And there's my solution to that equation. Right, if I plug that back in to check, now up here, 2 times 1 is 2, so 5 to the second power, which is 25. Then over here, when I plug in x equals 1, 1 plus 1 is 2, I also get 5 to the second power, which is also 25. Right? So again, because the exponential function is 1 to 1, because it only passes through each y value one single time, I know that if my outputs on either side are the same, and they have that same base of the exponential function, then I know the exponents have to be the same. All right, so that's a simple type of exponential equation. Most exponential equations are not like that. A lot of times, like if this was 5x equals 120 instead of 125, well, I can't write 120 as 5 raised to a power, and this method is not going to work. So now I have to use a different method, which I'll talk about in the next video I do, how to actually solve an exponential equation when it's not one of these simple types, right? So make sure you check out that other video that I'm going to do here. Because like I said, most exponential equations are not like this. They're of the more complicated type.